In this section, we're going to talk about finding the area inside a polar region. So I think the easiest way to kind of introduce this is to look at a circle. As you know from the last section, that circles are a polar region. And so, it's just an r equal to 2 or an r equal to 3 or something like that in polar form. So if we kind of think about that, the polar equation for this might be like r equals 2, radius equals 2, and it makes a circle. And so when we talk about finding the area of the circle, we can go back to geometry, and we know that area is pi r squared. And so when we think about what makes the equation here for the circle, r squared is just a radius squared, pi is half of the total number of radians in a circle. So when we talk about a sector here, just a sector here, then we're talking about an incremental area, delta A. And we can talk about this central angle here, theta. And so if this central angle is theta, then if we talk about this as being the portion of the sector, or the portion of the circle, then this is, for the entire circle, it's half of the entire circle times radius squared. So to figure out this area here, it's going to be half of that central angle times radius squared. And so that central angle then is really that incremental, we'll call it delta theta, that incremental change in central angle there. And so if we then go ahead and add up all these sectors from 0 to 2 pi in the case of a circle, but if we add up all those sectors, then we're talking about adding up all of these incremental areas. So we're talking about summing up all of these half r squared delta thetas. I know I'm changing the order in which I'm writing it, but it's all multiplication anyway. And so I'm going to do that for a specific reason, so that I'm kind of setting it up into a differential expression. And so as we add those up from the upper limit to the lower limit, that would be the same as saying a half as a constant. We can pull that out, and then we can integrate from some lower limit to upper limit. And when we talk about polar form and lower limit and upper limit, we start to use the Greek letters alpha and beta, because those refer to angle measures more commonly. So, and then it's r squared d theta. So in other words, we can get this expression where we can find the area, and we don't have to go back to the Cartesian definition of area as length times width. We can just go ahead and, since we know our function or our curve in polar form, we can get a polar form of the integral, or of the integral to find the total area. And so that happens to be this form here. We know that this is the curve in polar form, so we know that often that this is a function of theta as well. So we could also have an alternative way to write it, and that would be like that. For this polar curve here, I'm just going to go ahead and graph that just to kind of show you how it's generated on a graphing calculator. And so if we were to get in the appropriate mode here, go ahead and get into polar form and graph this 6 sine 2 theta. So 6 sine 2 theta. Oops. 6 sine 2 theta. There we go. And then go ahead and graph it. You can see it starts to make this four-petaled flower. So again, we have an even number n, so we get twice as many petals. There's a 2 and we see 4 petals, and radius of 6 means the length of this is 6. Hard to see when it's not along one of the axes, but that length is 6. So so here is that polar curve, and so we want to find the area of the region for one petal. So we're really only looking at this. So the question is how much of the curve do we have to trace just to get that one petal? And that means, really looking at where, we're starting at the pole and coming back to the pole. So how many radians do we have to go through to get back to the pole? We know the pole is a radius of 0. So we can look at this as saying, where is this a radius of 0? Where is our radius equal to 0, basically? And so that's when sine of 2 theta equals 0 over 6, but that's still 0. So that's when 2 theta, let's see, the sine is equal to 0 at 0 and pi, which means that theta then must be 0 and pi over 2, mathematically. So if we take a look at that then, and we can take a look at that here and trace this. So as we trace this, we're at a theta of 0. We're at 0, 0, so we're at the pole. And remember, we're tracing by pi over 24, which is these light gray radial lines. So there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you notice we get there when we're at pi over 2, or 12 pi over 24. We're back at the pole. And so that represents this. And so this is that first petal. Now if we want all of the times we go back to the pole, then we're going to have to extend this beyond the unit circle. So we would have to come back and say, well, we also have 2 pi and 3 pi, and that's going to get us our 2 pi over 2, which is our pi, and then our 3 pi over 2. I forgot to put a pi there. So that's going to get our next petal. And then we can keep going on then, because then we're going to have, that's going to be our 2 pi and our 3 pi, and then we're going to have our 4 pi and 5 pi to get this leaf. So as we go through there, then that's going to be our 4 pi over 2, which is going to be our 2 pi, and our 5 pi over 2, which is going to be our 5 pi over 2. Okay, and so that's going to get us our next petal, and so on and so forth. So we have to extend this out. Not that we're concerned about it, but just to kind of make a point there. And so dot, dot, dot to get that last petal. So, so we know then that we have to be between 0 and pi over 2. So if we're gonna go ahead and integrate then between 0 and pi over 2 to catch this first petal. So 1/2, and then our function is 6 sine 2 theta, and we have to square that, d theta. So what we're doing is we're integrating half from 0 to pi over 2 of 6, let's see, 6 squared is 36, sine 2 theta d theta. And for these, really, it's going to be an f-int. You're not going to be asked to do this without a calculator. These are all going to be f-ints. And the easiest way then to do the f-int is, as long as we have this in the graphing calculator anyway, the easiest thing is to do an f-int with your vars and grab this function, or not a function. I keep saying that it's not a function. Obviously, it doesn't pass the vertical line test. Grab this curve and stick it right into your f-int. So if we do our f-int, it's going to be an f-int, and then our function in polar form is 6 sine 2 theta, which is already in R1. So I'm going to go into vars and y vars and grab our polar function. and it's function r1, and then I'm going to go ahead and square it because it's r1 squared, which is this value. And then the variable of integration is theta, and we're going to go from 0 to pi over 2. Pi divide 2. And so when we integrate that, we get a value of 28.27. So we have half of 28.2743. And when we divide that by 2, we have 14.137 square units. Again, important to remember to round to three digits beyond the decimal point. Okay, in this one, this is a lemicon with an inner loop. It says find the area of the region bounded by a single curved inner loop. So we're looking at this here. So we have to figure out we have to figure out where we are at a radius again of 0. So when we're looking at this one, we're saying 4 minus 6 sine theta equals 0. And so our radius of 0 would be 6 sine theta equals 4. So sine of theta equals 4 over 6, or 2/3. So we're looking at a theta of sine inverse of 2/3. And so when we're talking about that, let's just kind of I want to be sure I'm in radian degree when I get these things, because integrating in degrees is not appropriate. So I'm going to do the inverse sine. So sine inverse of 2/3. And that is at 0.7297 radians. Okay, so if we think about that, just a quick unit circle here. So we're at 0.7297 radians. So that is like somewhere over here. Like, you know, this is pi over 2, and pi over 2 is 1.5. So this is about right here. And so that's the inverse sine. So where is the value then the same? And so we're going to have to look at where the value of the sine is the same, and that's going to be over here. And so if this is 0.7297 radians, then this is the same number of radians on the other side of pi over 2. So if that's the case, then if we take pi divided by 2 minus 0.7297, we get 0.841. So this is 0.841. So we need to be 0.841 on this side of pi over 2. So if we add pi over 2 to that, we end up at 2.412 roughly. So this other radian measure is 2.412. So that corresponds to those locations when the radius is when the value of this curve is equal to 0. And so that's going to be our lower bound and our upper bound. So we're looking at then, you know, if we would come back to here and graph this as 4 minus 6 sine theta, and we can do a zoom fit here. There we go. And so if we would go ahead and trace this, now these, I'm not sure if these are divisible by 24 or not, but let's go ahead and trace this just to see how close we can get. Notice when theta is equal to 0, we're out here, right? Sine of theta equals 0, radius is 4. So this is actually our starting point here. And then we come around here, loop there, so that's why this is not a value of theta equal to 0, because we've already looped through a certain part of this curve. So let's go ahead and 2, 3, 4, 5, 6. Yeah, so we're not hitting a radius equal to 0. It's not one that's divisible by 24. So this is definitely one that you're going to have to do by hand to find these these two values. The 2.4 isn't there, and the 0.7297 isn't there. Okay, so by hand is definitely the way to find these two. So we know that, oops, we know that our lower bound is 0.7297, our upper bound is 2.412. We're going to take half of this squared, so 4 minus 6 sine theta quantity squared d theta. And this is where using that vars function is going to really pay off, because I don't really feel like expanding that. So coming back to here, doing an f int, I'm just going to go ahead and grab my polar function out of the vars key. It's an R1, I'm going to square it. Variable of integration is theta, and then I'm just going to put in these decimals, 0.7297 and 1.4, or not 1, 2.412, 2.412. And then when I get the answer there, it's 3.5, so this ends up being half of 3.527. So taking this and dividing it by 2 gives us an answer of 1.764 square units. On this next one, it says find the points of intersection of these two curves. And so what we're going after here are these points here and here and here. And so really what we're saying is where are these two functions, or where are these two curves equal in value to each other. So all we're going to do is set these two expressions equal to each other. So we have 3 times 1 plus sine theta, and that equals 3 times 1 minus sine theta. And so dividing out the 3's, we get 1 plus sine theta equals 1 minus sine theta. And that gives us 2 sine theta equals 0, or sine theta equals 0. So where's sine theta equals 0? Well, that's 0 and 2 pi. And so we've got those two solutions, but we have 3 points of intersection, so we don't have enough solutions here. So the other thing you have to realize is that, well, if we plug these back in to r equals 3, 1 plus sine theta, and we plug 0 into here at theta equals 0, this is 0, our radius is equal to 3. So that's this point right here. And then when we look at the other function, 3, 1 minus sine theta, at theta equals 0, we get a radius also equal to 3. And then when we stick pi in here, excuse me, I accidentally wrote a 2 there, or maybe I even said a 2. Either way, it's wrong. This should just be pi. When we stick at theta equal pi there, we get our radius of 3. So that's over here, right? This is our pi line. So here's our positive 3 in the pi direction, or negative 3 in the 0 direction. And likewise, when I put pi into here, I get a radius of equal 3. So what I'm not getting is this. And so we could say by inspection, we also have a solution of r equals 0. And really what we need to do is we need to set this equal to 0 and figure out where those radian measures are. So we're going to go ahead and set r3 1 plus sine theta equal to 0. And if that's the case, then we have 1 plus sine theta equals 0. And so sine theta equals -1. And so where's sine theta equal to -1? That's at a theta of 3 pi over 2. So there's our other point. Now, if we look at this, 3 is 1 plus sine theta, 1 plus sine theta. The question is which curve is that? And so I'm not sure, so I'm just going to go ahead and graph it. 3 times 1 plus sine theta. And so when I graph that, it's the upper curve. So I actually got the color right. That's the red curve. And so the idea is the red curve starts here, and then at pi over 2, it starts here, comes all the way around to pi. So here's 0, pi, and then here's 3 pi over 2, and then back to the beginning. So that is the point, 3 pi over 2 is the point on the red curve. On the blue curve, then, change colors here, what we're really looking at is r equals 3, 1 minus sine theta. Where's that equal to 0? Because that's also the pole. And so that's 1 minus sine theta equals 0, or sine of theta equals a +1. And that is at pi over 2. So if we look at that, this is also the blue curve, the 1 minus sine theta. So let me just make that blue real quick. There we go. So when at theta equals 0, we're out here at 3. So here we are at a theta of 0 radians. And then here's our pi over 2. Here's our pi, which is this solution, and then coming back around. So our solutions then, we can look at those at as our 3 solutions here are at a theta of 0 radians and a radius of 3. So that would look like a radius of 3 and a theta of 0 radians. And then we have a radius of 3 and a theta of pi radians. That's those two. And then we have a radius of 0 and a theta of, at that point it doesn't matter which one you put because these are redundant. So we could either put this one or this one. It doesn't really matter which one you put as the third solution. Those 2 points are coincident. For this one, we want to find the common interior to these 2 dimpled limicons. And so the first thing we need to do is find these points of intersection. So the common interior is where they overlap. So it's basically this area here. So we need to find these 2 points of intersection. And in order to do that, we're just going to set these equal to each other. So 5 minus 3 sine theta equals 5 minus 3 cosine theta. And so we have really minus 3 sine theta equals minus 3 cosine theta. So where is sine theta equal to cosine theta? That's really what we're looking at. And so those 2 locations are pi over 4. And if we think about our unit circle again, right, sine and cosine, they have to either both be positive or both be negative, and then they have to be the same value. So here's where they're both positive, and here's where they're both negative. So that's our pi over 4, that's our 2 pi, our 3 pi, our 4 pi, and this is our 5 pi over 4. So it's those two locations where they have the same value. And so if we look at this, then what we have is as we sweep from this point to this point radially, we are going to sweep through the red function. So as we sweep through that point from there to there, we're going to sweep through the red portion of the function. And so that, being the red portion of the function, is only half the total shape. And so this ends up becoming, you can solve this a couple different ways, but it ends up becoming a situation where you have to either write this as two integrals, one for the red portion and one for the blue portion, or as I'm trying to show here, I'm going to copy and paste that area I just kind of colored in, and I'm going to change it to blue, and I'm going to try to flip it. So see if I can accomplish this. I'm going to flip left to right, and then I'm going to try to rotate it so that this lines up with this. So I'm going to have to do something like that. Oops, let me rotate a little bit more. There we go. And if we notice, then that fits right into the other half of the shape. So we have symmetry about this pi over 4 line, which is kind of cool. Not that we had to notice it. We could have done it in two integrals, but we have symmetry about this line. So if I just calculate the one red portion from pi over 4 to 5 pi over 4 and double it, I can get my answer. So I'm going to go ahead and set up the red portion. It's half from pi over 4 to 5 pi over 4 of the function. Now, which one is the red function? This one or that one? Well, I'm going to guess it's the cosine function because this is oriented on the x-axis here with the dimple up. But quite honestly, I really don't know. So I'm just going to graph 5 minus cosine theta and see which one comes up. And I guessed correctly. Let me get a standard window there. There we go. So actually it looks like I might have guessed incorrectly. Let me just square out that window. 5. There we go. Nope, I guessed incorrectly. You can't see the dimple there because of the resolution of the graphing calculator, but this one is actually the blue one. Good thing I checked. So that's actually the blue one, and so this is actually the red one. So I'm going to want to integrate that 5 minus 3 sine theta, quantity squared, d theta. So I'm going to go ahead and put this into the graphing calculator as 5 minus 3 sine theta. So I can prepare to integrate it. And so when I do an f int, then I can use my bars and not have such a difficult time squaring that. So out of y bars polar, I'm going to go ahead and grab my r1, I'm going to square it. I'm going to integrate it with respect to theta, and I'm going to have my lower limit be pi divided by 4, and my upper limit be 5 pi divided by 4, and when I integrate that, I get 50.25. So this is half of 50.25 0.251, which is equal to 25.125 square units. But that is just the red, so if I want the whole area, I'm going to have to double that, which means I'm back up to this number, 50.251 square units for the entire region.